Hello, everyone. Thanks for being here. I'm Gabriel. I'm a Senior Solution Architect at NVIDIA. Thank you, Sydney, for the introduction. I see a couple of you here who attended the workshop yesterday. So some of the slides will be similar, but I added some new ones. So don't run away. There are some new stuff that I added since yesterday. At NVIDIA, we are innovating every day. So we have some new stuff that just came out of the oven in the past couple of days. So I'm going to talk about those stuff. OK, so let's get started. We are talking about the new HPC market. And from our perspective, when people were talking about high-performance computing, normally they were referring to the what we are calling now traditional simulations, where you're using equations to actually simulate the world around you. But we are seeing more and more that the requirements for deep learning, machine learning, they're actually very similar to the ones that you have in traditional HPC. And just as a joke, if you look here, and I've just noticed that initially this conference was called HPC Advisory Council, and for whatever reason, they felt a need to add HPC-AI. From our perspective, is actually the same thing. So the requirements that you're having for deep learning, for machine learning, are exactly the same for that you have for traditional HPC. So what is NVIDIA doing, and how do we see this journey of new HPC market? We are working on different domains, and NVIDIA itself, maybe not a lot of you actually know, more than half of the engineers that are working at NVIDIA are actually software engineers. Obviously, the hardware and the chip, the GPU, is the foundation of all the work that we are doing at NVIDIA, and we're doing a lot of innovations in that field. But we are doing a lot more than that. And actually, today's presentation is going to focus more on the software side, on the innovation that we are bringing to the market on the software side, and the tools that we are putting in the hand of data scientists, of researchers, to actually get their code accelerated. So this is actually you can look at this as a summary of my presentation. So obviously, as I said, the GPU is still the foundation, the base for the entire, what we are calling accelerated computing. Obviously, it works in conjunction with the CPU. We're not saying that the CPUs will go away anytime soon. We're actually working with different type of CPUs, and you're going to understand later what I mean by that. And then we are doing a lot of innovation on the software stack. We have an entire ecosystem that we are putting together for HPC, and which includes not only standard libraries that are being used by researchers to build their accelerated software, but also deep learning libraries, machine learning libraries, and last but not least, we are trying to improve the productivity. The way you program and the way you actually refer to the GPUs has changed significantly over the past 10 years. So how do we do that? We are talking about the NVIDIA data center platform, and this is it's a very complex slide, and I'm going to try to walk you through. At the very bottom, as I said, we're still innovating on the hardware side, and if you look at the very left side, bottom left side, the chips and the GPU architecture is still there. We are integrating that in multiple solutions, whether we are talking about our own systems, which is the NVIDIA DGX family, or we are working with all our OEM partners or all the major cloud service providers. Basically, the availability of GPUs right now is actually pervasive. So, but that's just the hardware part, and as you can see, it's a very small component out of the entire platform. On top of that, you have the CUDA programming language, which we introduced more than 10 years ago. So now we are at CUDA version 10, And me personally, I actually started working with CUDA version 1. So we've came a long way ever since we first introduced the CUDA programming language. We enhanced the capabilities by adding libraries. We acknowledge that not everyone will actually be able or want to go that path to actually start programming in CUDA. So we made available a dozen of libraries and that number actually grew over time. And you can actually see in the next layer, there are a couple of them that are being mentioned, and now we are having different pillars. We have libraries for HPC, we have libraries for deep learning, libraries for machine learning, and I'm going to talk about a couple of them in the following slides. The next layer in what we are calling the data center platform is obviously the software. Whether, again, you're talking about traditional HPC where you have applications which traditionally were running on a CPU and are now accelerated on the GPU, so things like Amber and AMD, we're actually talking about more than 600 applications that are currently accelerated. So if you're a researcher, if you're a data scientist, most probably you're using at least one application that is being GPU accelerated. On the deep learning space, there's no one single deep learning framework that is not currently being GPU accelerated. So we are working basically with all the developers of deep learning frameworks to accelerate them. And last but not least, it's all the solution, all the good research, all the interesting research that is being done by guys like yourself, by your peers. We are working with universities, research centers, industries all over the world. And just to put it in perspective where accelerated computing is right now, we are actually powering the fastest supercomputer in the world, and you actually heard in the presentation earlier today being mentioned, Oak Ridge National Lab, the Summit supercomputer, has more than 27,000 GPUs in one single system. And it reaches a performance of 149 petaflops. And again, keep in mind this number because I'm going to refer to this number later on. And even the number itself, so for those of you who don't know, this is actually and I hope that everyone here knows because it's an HPC conference, this is the top 500 ranking. And this number, the 149 petaflops, it has actually been improved over the past 1.5 years in the last 3 releases of top 500. We didn't change anything in the architecture, we didn't upgrade anything in the hardware. All the work that has been done was done in software. And by improvements that we did in the libraries, in the CUDA toolkit, we managed to increase this number and get better performance out of the same architecture. We're also having the fastest supercomputer in Europe, the fastest supercomputer in Japan. And again, for those of you that think that HPC is only for academia and for researchers, I stand here to correct you. If you're looking there, industry is actually very much into HPC, and the fastest industrial supercomputer is again accelerated with GPUs. They have it's actually an oil and gas company, Total, in France, and they have more than 3,000 GPUs in their system. And we are also having, and I haven't put it here on the slides because I didn't want to steal the thunder from one of the presenters who will present tomorrow. So if you're sticking until the last presentation tomorrow, you're going to hear about the fastest supercomputer here in Australia, which is now powered by more than 600 GPUs. So if you're interested to hear more about that, please stick around tomorrow until the last presentation. The hardware, as I said, it's not everything. It's more about the research that we enable with the hardware. So those numbers, just the performance of a system, it doesn't mean anything. But the research that is coming out of that hardware is what makes the hardware have a meaning. And these are the finalists of the Gordon Bell Prize Award which were announced at Supercomputing conference last year. Again, if you don't know about Gordon Bell Prize, is actually like the Oscars in HPC. So if you're interested in getting your own Oscar, get a really nice research and submit it for the Golden Bell Prize. So these are the finalists, 5 out of the 6 finalists, and all 5 of them were actually using GPU acceleration for their work. And 2 of them actually got the big prize last year. And I'm not going to go into the details about the specific research that they're conducting. Each of these papers are very interesting in their own. But just take a look at for a little bit at the number that they achieved. So the first one is a research around genomics. The study itself is how about opioid addiction in the US, and they were achieving 2.36 exaflops in terms of computational power. With a small fine print, this was actually half precision, so we're not saying that we actually reach exascale. We are still a couple of years ahead of that, but we are heading towards exascale. But this research actually reached this astonishing performance. And as I said, all of them are very, very interesting in the research that they are doing. So maybe not all of you are actually at this level where you're doing or aiming for the Oscars in HPC. So for the rest of you, we actually have more than 600 applications that are already GPU accelerated. And you can actually take a look at the bottom of the slide. I put a link where you can download the apps catalog. I'm not going to go through all the applications that are here, but the reason for which I partitioned the slides like this is just to show you the breadth of domains where you have applications that are GPU accelerated. So whether we are talking about computational finance, climate weather, medical imaging, oil and gas, there are applications that are already GPU accelerated. So you just need to check if the application that you're currently using is accelerated and just start using it. For the rest of you who are more adventurous, as I mentioned, you have to go down the path of CUDA programming. CUDA, as I said, has been around for more than 10 years. We are now at version 10. The latest version of CUDA has actually been released less than 2 days ago. So if you're following the news, you would see that. And with each and every version, we are introducing new capabilities into the CUDA toolkit, which allows us to take more benefit and get more performance out of the hardware. Again, I'm not going to go into all the details, but I just want to point to you a couple of innovations that were introduced in CUDA 10. One of them is actually the support for the very latest architecture, which is the Turing architecture, and support for the new systems, things like NVSWITCH that I'm going to talk a little bit later. Another very interesting innovation that was actually slightly alluded by Rob in his presentation. The ability to actually control the execution through execution graphs. So now you have this possibility in CUDA to create CUDA graphs, which provide you the control over defining how the program will actually, the different components of the program will actually be executed. So a very interesting feature, which if you're a CUDA programmer, I highly encourage you to take a look at. Utilization of the Tensor cores. Those of you who know a little bit about the NVIDIA architecture, you probably know that one of the innovations in the latest architecture are the Tensor cores. We actually introduced capabilities to directly program those Tensor cores. A lot of innovation on the library side. Again, most of you might not necessarily want to go down the path to write your own code. The easiest way to accelerate your code is actually using libraries, and I'm going to have a couple of slides on that later on. And usability and ease of use of all these tools through developer tools that allows the developer to actually increase the performance of the application once you've developed your application, optimize the code. All these have been revamped in the latest version of CUDA. So because I mentioned libraries, one of the things that we introduced, and a lot of people thought that this is actually a new version of CUDA. You might have heard about CUDA-X. CUDA-X is nothing more than an umbrella for all the libraries that NVIDIA has been producing for the past 10 years. So CUDA-X is it's encompassing each and every library that we have available in the CUDA toolkit, which is spanning numbers domains from linear algebra to signal processing to deep learning, machine learning. And all these are now under this CUDA-X umbrella. And just to give you a couple of examples, again, things that have just been released in the latest version of CUDA. A lot of you who are doing deep learning, and especially deep learning using images, like segmentation, all those stuff. You need to process those images before you actually even start your deep learning pipeline. And we introduced this new library called NVJPEG that provides faster decoding of your images. Another library that, again, has just been introduced less than 2 months ago at ISC, cuTENSOR. Again, it's a new high-performance library that allows you to do tensor operation, like tensor contractions, element-wise operations. So all these things weren't available previously. So if you used to program in CUDA before, take a look at all these new advancements that we have and all these new libraries. And one specific thing for the guys who are doing research in signal processing, and here I'm referring to the astronomers. I know that POSI has a lot of users from the SCAP project, from the MWA project. We are working on a new library, CuFFT-DX, which is improving the capabilities of FFT's computations. Once again, if you know a little bit about NVIDIA libraries, you know that we already had an FFT library. This is an improvement over that, and it allows you to have massive improvement in performance. So if you're one of these users, I highly encourage you to take a look. And there's another one, cuBLAST MG. Just go to the link there. Right now, they're under early access program. You can take a look and register to get access to these libraries. So all these are they have just been released, so very, very new. As I said, we are also looking, or the GPU still remains an accelerator, and we are looking in pairing with all type of available CPUs to provide choices to the users. We don't want to constrain you to work with a specific CPU. So that's why we announced the support for CUDA on ARM. This will be available by the end of the year. We are working with our partners, ATOS, Cray, and HP on this. Again, it's a very exciting announcement. We got a lot of positive feedback in June in ISC when we did this announcement. As I said, we are also providing a lot of productivity tools, things like profilers, code analyzers. If you used before CUDA, again, we revamped all that. All this has been introduced in the latest version of CUDA. So I highly encourage you. I'm not going to go into the details, but take a look at the NSIGHT product family. And And again, if you're not really into CUDA, I'm not sure how many of you actually heard about this. We have something called OpenACC, which is a programming paradigm very similar with OpenMP. So if you ever did OpenMP, OpenACC will look very similar. You just put a couple of lines in your code, and if you have the right compiler, some magic will happen, and you will get your code accelerated, and it will run on GPUs. So if you don't really feel like learning CUDA, please take a look at OpenACC. So this is more on the HPC side. What we're doing on the AI side. First of all, we are claiming that we are the AI company. And we've been starting to work on AI for many, many years. And recently, a lot of people are actually thinking that, NVIDIA just has some, or is bragging about all the performance that we're having in our chips. If you're looking, have you ever heard about MLPerf? Show of hands, anyone? Oh, okay. So MLPerf is actually a new benchmark that has been put together by a consortium of companies, things like Google, Facebook, and they're actually accepting submissions from anyone in the industry to demonstrate the performance that they have, the capabilities at the chip level, but also at scale. So we did a submission last year when they first announced the benchmark, and we actually blew the numbers. We submitted for 5 out of the 6 categories, and we won all those categories. And this year we redid the submission, and you're going to see later on what the results were. So what we're trying to do is not just getting benchmarks, we are also looking at usability. So we put together NGC, NVIDIA GPU Cloud, which is basically a collection of containers that are optimized by the NVIDIA engineers, and we're making sure that you're getting the best performance out of it. And last but not least, as I said before, we are working on the end-to-end software stack. In the deep learning space, again, we have multiple tools that are available for both for development, both on the training side and on the inferencing side when you're talking about deployment. So let's take each of these components. And these are the results that we actually got for this year's submission. So this is the new version of the benchmark, so the 2019. As you can see, we're having some impressive numbers. And it's not that much impressive if you look at the numbers themselves, but just take a look at the comparison with the previous results. So bear in mind that we didn't release any new architecture in the past year. We didn't have new GPUs. On the exact same architecture that we had, which is the Volt architecture, just by improving the software, the libraries, the CUDA toolkit, and making improvements in the deep learning frameworks, in the entire stack, we managed to get an improvement sometimes up to almost 2x compared to the previous year. So this is to say that when you're investing in a GPU computing architecture, in a GPU solution, it's actually a long time investment. You're not just getting stuck because we're hearing that a lot of people are saying that, oh, you get the GPUs and then you get stuck with that. We are working continuously to make improvements, not just to the architecture, but to the entire software stack. And this is a statement or a proof for this statement. And how did we manage to actually get all this performance? We actually based everything on our internal knowledge, which translates, again, in years of building supercomputers, even inside NVIDIA. So we've been, you probably heard before about Saturn V, which was and it actually still is our biggest supercomputer in-house inside the NVIDIA data center, which has more than 600 nodes. But the results for this specific MLPerf benchmark were run on a new system that we put together, and which we're calling the DGX SuperPod. And this DGX SuperPod is actually having 96 DGX2 systems. I'm going to talk a little bit later about that. It's NVIDIA's system with 16 GPUs in one single system. And again, some impressive numbers, let alone the results that we got in MLPerf. We just run HPL on that system. We managed to get number 22 in the top 500. So very, very impressive for just 96 systems. And the best part is that you can actually get this system and you can implement it yourself in your own data center. So the foundation, and obviously there are a lot of components. There was a lot of work that went into this. We worked with Mellanox to improve the networking in between the nodes. We had to overcome a lot of difficulties. For example, imagine putting 4 of these systems in one single rack. So we are running racks at 45 kilowatts, which not a lot of data centers are actually capable of, or especially if you're in the an infrastructure guy, it's probably not something that you would be willing to do in your data center, but this is the future. So very, very high density. The building block for that, again, I don't want to focus too much on the hardware side, but the building block for that is the NVIDIA DGX2, which is a system with 16 GPUs, as I mentioned. But this is not necessarily the most important part. The innovation that we did with the implementation of this DGX2 is actually the introduction of NVSWITCH. NVSWITch allows us to actually interconnect all the 16 GPUs that you have inside of the DGX2 in an all-to-all network. So basically, any GPU can talk with any GPU at the maximum speed. So that allows us to basically get an increase in performance for the exact same number of GPUs. So what you're seeing here, the green line is actually the benchmarks that are being run on the DGX2, and the gray lines are actually benchmarks on 2 DGX1s. So basically 2 times 8 GPUs. So the exact same number of GPUs, but the advantage of NVSWITch is actually providing a lot of increase in performance. Obviously, we paired all that with the DGX software stack, which is mostly NGC. So once again, out of that, we distilled what we are calling the DGX pods, which are reference architectures for different industries. And we also worked with our storage partners to put together reference architecture. So all these are documented, and they're all available on the NVIDIA website if you're interested to take a look at. But again, MLPerf is just a benchmark. We actually went beyond that, and we are continuously innovating. Again, this is a result that we just announced a couple of days ago, where we managed to do a training for the BERT NLP network in 43 minutes. Again, this is a breaking record. If you're interested in the details, I highly recommend you to read the entire article that we published on the NVIDIA website. I also had, and we are acknowledging this convergence of HPC and AI, and I don't think I have to tell you more. All the previous speakers, almost, if I'm not wrong, almost everyone spoke about the convergence of HPC and AI. We think that this is the future, and there's no doubt that the advances both in HPC and AI will benefit each other's counterpart, and this will be the future. And that's why we are saying that the new HPC is actually traditional HPC plus AI plus machine learning. Another thing that we've been working on is automatic mixed precision. Again, I don't want to go into all the technicalities, but if you remember what Rob was presenting and even what Werner they were presenting, you can actually get similar performance when you're running your operation in lower precision, whether you are talking about FP16 or even INT8, especially for deep learning. And once again, you might think that this only applies for deep learning, but HPC is taking advantage of this research that is being done for deep learning. And again, remember that I told you at the beginning to remember this number, 149 petaflops for the Summit supercomputer, and this was an HPL run that we did for the latest submission. We actually did something more than that. And again, this is something that Rob mentioned. We worked with Professor Jack Dongara and his team, who's working on a iterative refinement solver that allows you to do computations starting in FP16, so half precision, and you get the same accuracy as FP64. So we did work with Jack Dongara. We implemented this, we took this library and we modified the HPL code, and we got what we are calling HPL-AI, which is basically a mixed precision HPL. And we run this code again on Summit. And with this code, we actually managed to get 445 petaflops. So again, a lot of research that is being done into this space. As I said, on the usability side, we are putting together NGC, NVIDIA GPU Cloud, which is nothing more than a container, a collection of containers. But the good part is that we are actually having a couple of dozens of engineers who are working in optimizing this. So now we have a monthly release cycle for the containers, and with every release, we are actually increasing the performance. There are a lot of other goodies in NGC. We now have pre-trained models. We have model training scripts. I'm going to let you discover all the goodies. Just keep in mind one single address, ngc.nvidia.com. I highly encourage you to take a look. And it's not just for deep learning. We have HPC application. We have visualization applications. We have entire workflows that we put together. This is just one of the examples. For healthcare, we have something called NVIDIA CLARA AI, which is a framework for medical imaging. And this, you can actually refer to the link at the bottom of the slide to learn more. And again, this is a very new release that we did a couple of months ago. And we already have a success story right here. So we've been working with Sydney Neuroimaging Analysis Center, obviously in Sydney. And they're already implementing this in their workflow. And they're getting some pretty good results. And as I said, the commitment is to actually get the performance. So month over month, our engineers are hard at work to actually get you the best performance into those containers. So I highly encourage you to take a look at the container. And last but not least, because this was the last part, I was talking about HPC deep learning. So the last part, machine learning. We've been very active in this field too. This is how a traditional machine learning workflow would look like. And what we've been hard working on is the RAPIDS framework. The RAPIDS framework is a collection of libraries. Again, remember that I was talking about CUDA-X. All these libraries are part of the CUDA-X initiative. But the whole RAPIDS framework is an open source project that is hosted on GitHub, so anyone can contribute. We are having libraries that are very similar with pandas and scikit-learn. So all the machine learning guys in the room probably know what I'm talking about. If you're doing traditional machine learning, you'll find that all these libraries have very similar Python APIs. So I highly encourage you to take a look at it. And just to convince you why you should do that, these are a couple of numbers that shows the benefits, both for the data loading and preparation, and also the machine learning training. Just take a look here, an order of magnitude improvement. And I think that that says a lot. And last but not least, there was some discussions previously about GPU Direct RDMA. And a lot of workloads, both on the HPC side, deep learning and machine learning side, are now dependent on the data. So again, this is something that we've been working recently called GPU Direct Storage, which allows to ingest the data directly from the NVMEs into the GPU. So again, it will bring a lot of advantage for all the three domains: traditional HPC, machine learning, and deep learning. And once again, this is something very, very new. It's not yet available. We are working with a couple of customers, and we will probably have a better release for this towards the end of the year. But if you want to read a little bit more, again, you have the address there. So just to conclude, because I think I'm way over time, NVIDIA is an entire platform. So again, you've heard in the morning that a lot of people are coming up with chips that are claiming to do training or inferencing. Coming up with a chip, it might be easy, but you have to build the entire platform, the entire ecosystem around that. And NVIDIA has been doing that for the past 10 years. Usability, everything is packaged inside NGC. And availability of the GPUs from your desktop all the way to the data center. And again, I refer you to all the DGX pod and the DGX reference architectures that we put together, which stand as a proof of the work that we are doing internally. And with that, thank you very much for your attention.